Imagine standing on a coastline, the air thick with anticipation. Before you, bathed in brilliant floodlights against the pre-dawn sky, stands a colossal machine. It is a monument to human ambition, a tower of metal and fuel pointing directly upwards, challenging the very heavens. This is the scene of a rocket launch, a spectacle that has captivated humanity for decades. The ground begins to tremble, a low rumble that grows into a deafening roar, a sound so powerful it feels less heard and more experienced, vibrating through your very bones. It is the sound of immense power being unleashed, a controlled explosion designed to do one thing: defy gravity. Flames, brighter than the sun, erupt from the base of the rocket. For a moment that seems to stretch into eternity, the rocket remains tethered to the ground, straining against its restraints as its engines build to full thrust. Then, with a final decisive surge, the clamps release. Slowly, almost majestically, the giant machine begins to rise, inch by painful inch, as if lifting the weight of the world's dreams on its shoulders. The ascent accelerates, the initial crawl transforming into a determined climb. For those watching from below, it is a moment of pure awe, a testament to what we can achieve when we unite science, engineering, and sheer determination. But behind this breathtaking display of power lies a fundamental and brutal challenge. Let us consider the sheer audacity of the task. We live at the bottom of a deep gravity well. The Earth's gravitational pull is relentless, a constant force that holds everything and everyone firmly to its surface. To escape it, an object must achieve an incredible speed, known as escape velocity. For our planet, that speed is approximately 11.2 kilometers per second. That is over 40,000 kilometers per hour. Think about the most powerful vehicles we have on Earth. A Formula One car can reach speeds of around 370 kilometers per hour. A commercial jetliner cruises at about 900 kilometers per hour. This is where the rocket comes in. Unlike a car, which pushes against the road, or a plane, which pushes against the air, a rocket has nothing to push against in the vacuum of space. It operates on a principle first articulated by Sir Isaac Newton. This creates a cruel paradox. To go faster, you need more fuel, but adding more fuel makes the rocket heavier. A heavier rocket requires even more fuel just to lift the extra weight of that fuel off the ground. Let us look at a famous example, the mighty Saturn V. This was the rocket that carried humanity to the moon during the Apollo missions. It stood over 110 meters tall, taller than a 36-story building. At launch, it weighed a staggering 2.9 million kilograms. Yet when you look at what it was designed to deliver to the moon, the numbers become almost comical. The useful part represented just 1.5% of the rocket's total starting weight. Imagine packing for a holiday and finding that your luggage consists of a single pair of socks, while the rest of the volume is taken up by the suitcase itself and the petrol needed to get it to the airport. This is the absurd reality that rocket engineers face every single day. To understand the rocket equation, we must first meet the man who dreamt it into existence. His name was Konstantin Tsiolkovsky, a figure whose life was as remarkable as his scientific contributions. Born in 1857 in a small village in the Russian Empire, Tsiolkovsky's early life was marked by hardship and isolation. At the age of 10, a severe bout of scarlet fever left him almost completely deaf. Unable to easily communicate with those around him, he turned to books and his own imagination for company. Tsiolkovsky became a dedicated and brilliant autodidact, devouring complex scientific texts on his own. This solitary study ignited in him a deep and abiding passion for the cosmos. He was not just interested in the stars as distant points of light. He was obsessed with the idea of humanity traveling amongst them. It was in 1903, the same year the Wright brothers made their first flight at Kitty Hawk, that Tsiolkovsky published his most important work. It was titled Exploration of Cosmic Space by Means of Reaction Devices. In this seminal paper, he laid out, for the first time, the fundamental principles of rocketry. And buried within the text was the mathematical jewel of his life's work, the classical rocket equation. So what does this famous equation actually look like? In its most common form, the Tsiolkovsky rocket equation is written as delta-V equals V sub E times the natural logarithm of m0 over m1. Think of delta-V as the currency of space travel. Every maneuver has a specific delta-V cost. To get from the surface of the Earth into a stable, low Earth orbit, you need to spend about 9.4 kilometers per second of delta-V. The next part of our equation is V sub E, which stands for effective exhaust velocity. This term represents how fast the rocket can throw its own mass out of the back. You can think of this as the efficiency of the rocket engine. The engines on the Saturn V rocket, which burned a mixture of highly refined kerosene and liquid oxygen, had an exhaust velocity of about 3 kilometers per second. Modern engines that burn liquid hydrogen and liquid oxygen can achieve exhaust velocities of around 4.5 kilometers per second. Now we come to the final, most brutal part of the equation. ln of m0 over m1. Because the mass ratio is inside a natural logarithm, it has a diminishing effect on the final delta-V. Let's say your mass ratio is 3, meaning 2/3 of your rocket is fuel. If you want to double your delta-V, you cannot just double your fuel. Because of the logarithm, you would need to square your mass ratio, requiring a new ratio of 9. The rocket equation mercilessly exposes the central dilemma of spaceflight, the problem of carrying your own fuel. Let's try to visualize this compounding problem. Picture a hiker who wants to walk across a desert. The water needed to carry the water quickly outweighs the water needed for the actual journey. This is precisely the situation rocket engineers find themselves in. The most fundamental solution, first proposed by Tsiolkovsky himself, is staging. By breaking the journey into steps and discarding massive empty fuel tanks, we essentially reset the rocket equation partway through the flight. Today, the battle against the rocket equation continues, but the strategies have evolved. The rise of commercial spaceflight has brought a renewed focus on reusability, but with a different approach than the shuttle. To push beyond chemical limitations, engineers are exploring more radical ideas. Ion engines use powerful electric and magnetic fields to accelerate ions to incredible speeds, often 10 times the exhaust velocity of a chemical rocket. Looking to the future, ambitious projects like SpaceX's Starship are attempting to tackle the equation head-on through full reusability and orbital refueling, effectively resetting the rocket equation for interplanetary journeys. From a deafened, self-taught schoolteacher in a remote Russian village to the towering launch pads of the 21st century, the Tsiolkovsky rocket equation has been the silent, unyielding dictator of our journey to the stars. The equation tells us how hard the journey is, but the existence of rockets themselves, and the footprints left on another world, tell us that we are willing to pay the price. The tyranny of the mass ratio is formidable, but the power of human ambition has proven to be an even greater force. The future of humanity in space will be written by those who continue to find innovative ways to work within this enduring law. It's a testament to our relentless desire to explore, to push beyond our limits, and to reach for the seemingly impossible. One that will continue to propel us upwards, towards the endless frontier.